Hello everyone, welcome. This is a time of class for the ECE317 digital signal processing. This lecture is for the 6 weeks Wednesday's class. Alright. And today we will discuss how to solve the difference equation with the multiple poles or complex poles. Alright. So let's go to here. ECE317 for the 6-week Wednesday class. We try to solve difference equation with multiple poles or complex poles. Yeah. Okay, first one for the multiple poles. I use an example to explain it. Alright. Yeah. Okay. Example. We consider a system with equation y of n minus y of n minus 1 plus 1/4 y of n minus 2 equal to x of n. Suppose the system has equation looks like this, and so we want to find the solution. We want to find all possible solutions. All possible solutions. Okay, so actually we know y or of n, it should be yh of n plus yp of n. So we need to find these two. For yh is a solution of the homogeneous equation, and for yp is a particular solution. Oh, I need the input. If input is 1/3 to the n u of n. Okay, I have several steps. Step 1, yp. We start from the particular solution. What is this? Okay, this one. One has frequency response. Right, we can find the frequency response. H of e to the j omega, that will be 1 over 1 minus e to the negative j omega, and plus 1/4 e to the negative 2 j omega. And actually this is what? This is 1 minus 1/2 e to the negative j omega square in the denominator. In this one. So this is an example for we have multiple poles. Pole is 1/2 multiple 2. Multiple 2. Okay, then what is the output? The the output in frequency domain, it will be the frequency response times the input in frequency domain, and it is 1 over 1 minus 1/2 e to the negative j omega square. I just copy it, and x is given here, right? So in frequency domain it will be 1 minus 1/3 times the exponential power. So here is a 1 minus 1/3 e to the negative j omega 1. Right? So this is y. This is y. We want to go back to time domain. Suppose y equal to, okay, you need to separate these two. 1 minus 1/2 e to the negative j omega squared plus 1 minus 1/3 e to the negative j omega. Here you need a. Okay, not enough because the denominator has other 2. So numerator you need one more term, a plus b times e to the negative j omega. If here's a square, if here's a cube, then you need even more term in the numerator. Alright, now we have order 2 in the denominator. The numerator will be order 1. 1 less than the denominator. Right? Denominator has order 2. The numerator has order 1. And this side will be c. Second term c. Actually, this is also same rule. Same law. Denominator has order 1. So numerator should be order 0. Alright. Now of course you need a requirement. This one must be a primer fraction. If here you have some numerator term with order more than 3 or more, you cannot work like this. Alright. We will discuss that kind of things for after we study the Z transform. Okay, now let's add these two terms together, these two fractions, right? Add two fractions together. Then the denominator should be a multiplication of denominator of each. So this is the first term, this is a square, and the second term, okay, this is 1 minus 1/3 e to negative j omega. This is the first order term. And the numerator, we need to times them crossly and add them together, right? So the first one is a plus b e to the negative j omega times 1 minus 1/3 e to the negative j omega. And second term is c times 1 minus 1/2 e to the negative j omega squared. Alright, and just times them. Here's a plus b e to the negative j omega times 1, right? Times 1. And then times negative 1/3 of this one. So I have negative 1/3 of a e to negative j omega, and the negative 1/3 b e to the negative j omega squared, right? I have 2 of these e to negative j omega. And the plus c, this is a square of the, so the first term is still 1, right? 1 square is 1, so 1 times c. And the second term should be 2 times each, so 2 times 1 times this, I get 1, it's negative 1. So negative 1, here just c, right? C, e to the negative j omega. And last term will be the square term, that will be 1/4 and c. So this is 1/4 times c. This coefficient, and the power is e to the negative j omega with square. Alright, the denominator is the same. Denominator is the same, just copy it. Then you see, we want this fraction equal to y, right? This is y. Y should be this one. The numerator is just 1. Now numerator is a combine of all of these. So we want all of these, do the summation, it will be 1. Then we have, okay, constant term, we have a, we have c, right? Two constant, so a plus c, that should be 1. It should be 1. And then first order term, this is a negative 1/3 a, and this is a negative c. Okay, should be 0, right? We do not have e to the negative j omega here. It is just 1. And then the square term, I have negative 1/3 b plus 1/4 c. This is also 0, right? Because in the numerator, no term with e to the negative j omega 2, right? We do not have this kind of term, so this coefficient must be also 0. Okay, now we can solve it.
which one will be? Yeah, we can try to find A and C firstly and plug in C to get B, right? So this one we get C equal to -1/3 A, and then these two I have A times 1 minus 1/3 equal to 1. So A times 2/3 equal to 1. Then A is 3/2, right? 1.5 is it A. Then C, right? We have C, right? So we have C is -1/3 times this is -1/2. We have C. And then B is here. B, we have 1/3 of B equal to 1/4 of C. So B is 3/4, 3/4 times C. And C is -1/2, so this is -3/8. Oh, am I good? Yeah, should be good. Okay. Now we have A, B, C, right? So we have y equal to this one plus this one, and let me separate the first fraction. I copied, but I separated the first fraction in 3 terms. There will be A, that is 3/2 over 1 minus 1/2 e to the -j omega squared, plus B is here negative, oh it should be minus, okay, -3/8, right, I put negative here, and 1 e to the B, what is e to the -j omega, and 1 minus 1/2 e to the -j omega squared, and plus C, space enough, C is -1/2 over 1 minus 1/3 e to the -j omega. Alright, so we have these 3. Then we need to use a table to find what is the time domain, right? We need to go back with dtft inverse. We will have y of n equal to, okay, we need check tables again. We need check tables. Okay, the square term is here. This is 6th term in the table, right? The square term according to that one. So, okay, square term, here's a to the n and n plus 1 in front. So it is the first one. I have 3/2 is a coefficient. Then I need a n plus 1 times that a now is 1/2 to the n u of n. Right, this is the first term. And second term minus 3/8. Okay, we have square term again, so we will have similar term like this. But we have e to the -j omega multiply on it. Then what is this? This one in time domain it will be a shift. Remember? Yeah, we have another table. For the transform table, we have these. This will be a give a shift in time domain. So now this part will be this one with a shift on time. Now how many shift? This is negative e to the j omega, then shifted by 1. So we will replace n by, okay, let me write it here. This one go to n to be replaced by n minus 1. Alright, so we just rewrite this part, but use n minus 1 to replace n. So n minus 1, here's n is n minus 1, then this is just n. And this is 1/2 n minus 1. And u of n minus 1. to the table again. Square term. We have shift by, in the frequency domain we times these. In time domain, just replace n by n minus nd. Here nd is 1, right? In our example, nd is 1. Okay. Now we have the first two terms. And last term is 1 minus 1 half, sorry, not 1 minus, minus 1 half. And this is 1/3 to the n u of n. Okay, so this will be the answer. And we can do some simplify. You look at this one. Here's a u of n minus 1, right? The other two terms, they are u of n. But we have n in front. So we notice this one. We notice n times u of n minus 1. When n is 0, this is 0. And n times u of n, when n is 0, it is also 0. So these two are same. These two are same. Yeah, these two are same. So this one we can just replace u of n minus 1 by u of n, because I have n in the front. I can do this. In generally, u of n minus 1 and u of n are different, but here they are same thing. Then all of them we have u of n. This is the first thing we can do, simplify. Second thing, you see here's n plus 1. Here's n. So we can separate n plus 1. Then first is n, second is just 1 times it. And the first n combined with these. So I can have the term n times this one as one term. And no n times this one as another term. Okay. So we can do like this. This is the term with n. There will be 3 over 2 minus 3 over 8 times n, right? Both contain n. And 1/2 to the n u of n. And another part is 3 over 2, no n term, right? Here is just 1/2 to the n u of n. And last term minus 1/2, 1/3 to the n times u of n. Alright, need to add these two together. This is how many? Times 4 in the both numerator denominator. That will be 12, right? Times 4 times 4. So denominator will be 8, numerator will be 12. 12 minus 3, I get 9, right? 3, 4 is 12. 12 minus 3 is 9. This is, and this is n, and 1/2 to the n u of n. Second term is 3 over 2, 1/2 to the n u of n. And last one is 1/2, 1/3 to the n u of n. Alright, so this is the particular solution. Actually, this is we get a solution of y based on the Fourier transform. Right, this is particular solution. Yp here. Alright, after we have the particular solution, we try to find the homogeneous solution. This is step 2. Step 2. We need to find the homogeneous solution. Yeah, what it is. We know the homogeneous solution will satisfies the homogeneous equation. So this is just the original equation, but remove all the x terms. So it is this one. It's plus 1/4. Yeah, see. So remove this x to be 0 and keep this part. So minus 1 plus 1/4. Minus 1 plus 1/4. Okay. Y of n minus 2 equal to 0. It is this one. And then let y equal to some lambda to the n's. Now we do not know what is lambda. We want to find lambda. Then plug in, we have lambda to the n minus lambda to the n minus 1 plus 1/4. Oh, here's a minus, here's plus, yeah, plus 1/4. Lambda to the n is now n minus 2 equal to 0. We can remove these out, right? So lambda to the n minus 2 times lambda square minus lambda plus 1/4 equal to 0. So it is just this one equal to 0. Right? This one equal to 0, so lambda equal to, we can just use the formula, right? It will be negative b, there will be 1 plus or minus square root of b squared minus 4 times a times c over 2 times a. Alright, this is 1 plus or minus square root of, okay, this is 0, right? 4 times 4 is 0, is 1. 1 minus 1 is 0 over 2. You see, this is just 1 over 2. One solution. We only have one solution. Then we know y homogeneous solution were equal to, okay, sum r times 1 over 2 to the n's. Is it good? Well, see, it's not enough because this is second order system. So here should be two terms. We only have one term. What will be the other term? Okay, just look at the solution here. This is homogeneous solution. Homogeneous solution, according to that root 1/2, we have two terms. One is this, 1/2 to the n term times n, and this is 1/2 to the n term, right? We have both related with 1/2. The difference is here, we have more terms times n in front of it. Okay, it is just this one. Here we need, this is alpha 1, and second term we need alpha 2 times this one. It is n times 1/2 to the n. That's it. Alright, actually here you can do this directly. After you get the particular solution like this, then the homogeneous solution will just be these two parts. Remove u of n and add the constant, arbitrary constant in front of that. That will be the homogeneous solution. Now of course you need to know which part will move to here. Like this 1/3 you cannot move to here. This 1/3 is coming from the input. Now we use input is 0. Right? Input is 1. Input is related with 1/3, right? 1/3. So this 1/3 term is coming from input, and these two terms coming from the system itself. But of course, you know, here you solve by partial fraction, you find these two coefficients. But sometimes maybe we can have the case one of these two numbers will be 0. Yeah, it could happen, right? Sometimes, depend on the system. Then here you will only have one term, so you directly work from here. Sometimes works, sometimes doesn't work. And here you just start from here, no problem. You always work. Alright. Why we have this term? Because this is a multiple 2. Multiple 2. It's multiple 2, so we have one more term. If here is like a multiple k, then you need more terms. Alright. Okay, so this is a homogeneous solution. Alpha 1, alpha 2, they are arbitrary numbers. Any numbers. Any numbers can work. Any numbers can work. And here I will say if h of e to the j omega has a pole lambda with multiple like a q, then y, homogeneous y, will have has terms, the following terms: alpha 1 times lambda to the n plus alpha 2 times n and lambda to the n, and alpha 3 with n squared lambda to the n, until the last one, alpha q, the n to the q times lambda, minus 1, q minus 1 times lambda to the n. We'll have so many terms, totally q terms. Right, q terms, totally q terms. Totally q terms. So you have a pole with multiple q, then the homogeneous solution will contain q terms. Alright. Okay. Then we can have our step 3. Step 3, all the possible solutions of the equation. There will be y r of n equal to a particular homogeneous. I put homogeneous in front. Homogeneous solution, that is alpha 1 times 1/2 to the n plus alpha 2 n times 1/2 to the n, and then the particular solution plus, okay, for convenience I can this is a particular solution, right? I can move this in front because the first term is 1/2 to the n, right? Second with n here, I already put the n here, so I use the same order. The first one is 3 over 2 1/2 to the n u of n, and the second term now is 9 over 8 n times 1/2 to the n u of n, and then last one is minus 1/2 1/3 to the n u of n. Okay, so this is all possible solutions of the equation. Then if we have initial condition, you can plug in the initial condition, try to determine alpha 1, alpha 2, then you can have a final answer, satisfy the equation and the given initial condition. What do you think? Right? Okay, then what is the original problem? Okay, I didn't give the initial condition, so just as it is. So this will be the answer. All right, this will be the answer. Okay, so this is the case with multiple poles. And next, let's consider the case with complex poles. This complex poles. And I also use an example to explain it. Oh no, before example I need to do something. Okay, the system is a real system. Real system. So that means summation ak times y of n minus k equal to summation bk times x of n minus k. All these ak, bk, they are real numbers. Right. ak
bk, real number. Okay, in this case, they will say, then if lambda equal to a plus bj is a pole, then we will say another lambda. I say lambda star. Okay, usually people like to put a star here. By a complex number means a plus a minus bj is also a pole. So for complex poles, a plus bj and a minus bj, they always occur at the same time. If you have this one, then you must have another one as a pole. If you have this one, you also have that one as a pole. They always occur as a pair. Okay. Now YH of n will contain term. We say a plus bj to the n with a coefficient and a minus bj to the n with a coefficient. What are these two coefficients? We wanted the whole result to be a complex, to be a real number, not complex number, to be a real number. We wanted it to be real number. The whole thing must be a real number. Real number. You have to cancel those terms with j. Okay? You have so many terms here. Some with j, some without j. And this is also some with j, some without j. If you only have these two, the j term, they can be cancelled. But now we need to put some constant in front of it. So what kind of constant can we have? Okay, actually we have two choices. We can have real part and an imaginary part. Like this, right? Then this side, we also need to put a and minus bj. Why? You see, the term with j just the opposite. They just reverse the sign, so they can cancel. If here you put a positive or something else, you cannot cancel them. And another thing is we can only have two free coefficients in this form. So now we have two, right? So that's enough. Okay, so it will be this. Here a, b, they are any real numbers. They are any real numbers. They are real. They are real. Alright. So for homogeneous part, we have this one. We have this one. Now we look at an example. We have y of n minus y of n minus 1 plus, now is now 1/4, 1/2 y of n minus 2 equal to x of n. And I still use input x of n equal to 1/3 to the n u of n. We want to find our possible output or possible solution. Then we still use the formula. We know yr will be yh plus yp, right? So we can solve. Okay, this time we start from yp. Okay, step 1. What is a yp? I still use that from yp of n equal to what? I want this. Okay, similar way the last example, we have h of e to the j omega, the frequency response. It will be, okay, you just plug in 1, right? This is just 1. X of n, nothing changed, just 1. And the denominator y, first term is y of n, nothing changed. And the second one we have a delay. And the last one we have half of the delay 2 steps. Okay, this is h. And we can separate these as 1 minus 1/2 e to the negative j omega square plus 1/4 e to the negative j 2 omega. I can write it in this way. Make sense? This square, you have 1 and 2 of these is this one, right? And then square of this is 1/4. Square of this is 1/4. And here's another 1/4. So you have 1/2. Right? 1/4, you get 1/2. Alright, so this is h. This is h. Now what is the pole? You want put this, actually if you want to write more, this will be 1 minus 1/2 e to the negative j omega minus 1/2 j e to negative j omega times 1 minus 1/2 e to negative j omega plus 1/2 j e to the negative j omega. Yeah, actually this one. The pole is you need these two, right? This give pole 1/2 plus 1/2 j, and this give poles. The give pole is a 1/2 minus 1/2 j. So we have two poles, but they are complex. Find particular solution. Yp of e to the j omega will be frequency response times input in frequency domain. That will be 1/3 to the n, not to the n. That is that. It's 1/3 to the n. So 1 minus 1/3 e to negative j omega 1 is this one. Right. So yp is a multiplication of this one, and this one. We have three terms. Now suppose we use partial fraction. Y equal to a over 1 minus this one, right? This one. And the last two terms I can combine them together. That is 1/2 minus 1/2 j plus 1/2 j and e to negative j omega. And second term is b over 1 minus 1/2 minus 1/2 j times e to negative j omega. And last term should be this one, right? So c over 1 minus 1/3 e to negative j omega. This is multiple, right? Times, not x. Okay, suppose y equal to this, and we put all of these together equal to that one, equal to this one, equal to this one. So numerator must be 1. If you combine these three terms together, the numerator must be 1. So I just write the numerator. A times these two. Okay, just copy, right? A times these and times these. This is A. And the B plus B times this one and this one. So 1 minus 1/2 plus 1/2 j times e to negative j omega, and 1 minus 1/3 e to the negative j omega, and then C times that 2. That will be 1 minus 1/2 plus 1/2 j e to negative j omega, and 1 minus 1/2 minus 1/2 j e to negative j omega. Okay, we have these three. These three to summation, it should be 1. Right, numerator must be 1. Okay, now we compare the both sides. We want the constant must be 1. the term with e to the j omega must be 0. The terms with square of e to the j omega still be 0. Okay, so we can have constant term a times 1 times 1, b times 1 and 1, c times 1 and 1. So that is just a plus b plus c equal to 1. Then the coefficient of e to the j omega, a times a negative of these, right, times 1. So I have a negative of 1/2 minus 1/2 j. This is one term. I times these two together. I use this as coefficient. And I times these two together. I have another term with e to the j omega. The coefficient is negative 1/3. Okay, that's it. So this is the coefficient of e to the negative j omega in the first term. And then for b, we have similar thing. That will be b times, okay, this one now is negative 1/2 plus 1/2 j. Right, this one times 1, I get this, and minus 1/3. Okay, and the c term similar, plus c term, this one times 1, I have negative 1/2 plus 1/2 j, and these two times together I have another negative 1/2 minus 1/2 j. Okay, so this gives us the coefficient of e to the negative j omega in the c term. Alright, summation should be 0, right? Because this side is the right side, we only have 1, no exponential power of omega. And then we check the square term, e to the negative j omega squared. So I have a, this is 1 times this one, this is 1, right? I have this one times this one, this one times this one. They have the term, this is a term with e to the j2 omega, right? E to the negative j2 omega. And coefficient is this one times a. So it's a times, okay, negative times, then cancel to be positive. So it's this one times 1/3. It's 1/3 of 1/2 minus 1/2 j. And then b term, we still check the square term. Square of exponential power is these two. So I have positive 1/3 times 1/2 plus 1/2 j. And c term, for square I have these two. So I have 1/2 plus 1/2 j and 1/2 minus 1/2 j. And the coefficient before them is negative and negative, that's 1. Okay, I have this, must be 0. Alright, we have the equation. Here the equation looks long, but it's not difficult, you know. You just work step by step, you can have the answer. First, of course, we need some simplify. A plus b plus c equal to 0. And this one, a, b, c. So this one is a times negative, I get 5/6, right? Half and 1/3 is 5/6, and plus 1/2 j. This is the a coefficient. And the b with coefficient negative half, negative 1/3 is still negative 6/5, and minus 1/2 j. And c now is a negative, I get negative 1, and negative 1/2 j and positive 1/2 j, they cancel. Okay, it's 0. And third equation, it is a. Okay, yeah, these two you already have, so I just move coefficient in the front. 2, 3 is 6, right? 6. 1 minus j over 6, right? 1 minus j over 6 times a. And this is a 1 plus j over 6 over times b. And this is a c, I need to multiply. C, the coefficient is, I put the coefficient in the front, it is 1/4 minus 1/4 j plus 1/4 j and minus 1/4 j squared equal to 0. So this is a long problem. Okay, it will be a plus b plus c equal to 0. And a times, I put coefficient in front, -5/6 plus half j times a, and -5/6 plus half j times b minus c equal to 0. And this one is, okay, I still separate this, real and imaginary might be better. 1/6 minus j/6a and plus 1/6 plus j/6b plus, oh, here's a c, that's the c. Here's these two cancel, right? And j squared is -1. J squared is -1. J squared is -1, so here's a plus 1/4. Here's a plus 1/4, so plus 1/2. 1/2 c, right? These two cancel. 1/2 c. This will be 0. This is a 1, 2, 3. 1, 2, 3. Yeah, maybe we need a MATLAB. Okay, we can use MATLAB to solve the equation. Three orders and complex numbers. All right. We have 3 unknowns, A, B, C. Yeah, we see the balls. Let me see the balls. I think I got something wrong. This one. Oh, sorry. Yeah, I just think I got something wrong. Sorry. This one is good. But when I write this one to this two here is good. This one should be minus. Should be minus. Right? This is minus good. This is a good. It's a 1 minus and 1 plus. Okay, so this should be minus. This is not good. Yeah. Okay, we try to solve these. You can see the equation, right? I use a equal to, I put a coefficient in a matrix. The first row will be just 1, 1, 1, right? The a plus b plus c is 0, so this 1, 1, 1, the first row. And second row is -5/6 plus 1/2 times j. Right? And the second coefficient is -5/6 plus minus 1/2 times j. And the last coefficient is -1. Okay, we have the second row, 3 coefficients. And the last row, I have 1/6 minus j/6. And the second coefficient is 1/6 and plus j/6. And last coefficient is 1/2. Okay, we have a. Or the computer calculate, find the exact values. This is a, not exact value, approximate value. Okay, this is a. And I want this is not 0. It should be 1. Sorry, ABC is 1. ABC is 1. A plus B plus C is 1. Sorry. So the other side I have a B is 1 0 0. Alright, this is B, and the result will be inverse of A times B. Okay, this will be the answer. Okay, so we have A, B, C equal to that matrix A inverse times 1 0 0. Right? Yeah, as I showed here. So it is here result is 0.3 plus minus 0.9 I, 0.3 plus 0.9 I, and 0.4. Now I is J here. I use J. Okay, so I have ABC. I have ABC. Then we can have Y is here, right? Y is here. Capital Y is here. In frequency domain is this one, and now I know the coefficient ABC. So I just plug it in and go to the time domain. I have Y particular of n. That will be A is 0.3 minus 0.9 J times power of these 1/2 plus 1/2 J to the n U of n, and B is 0.3 plus 0.9 J 1/2. Now this is a minus 1/2 J and U of n, and last term is 0.4. Okay, 0.4 times this is 1/3 to the n U of n. Okay, so this is the particular solution. All right, and then homogeneous solution. Step 2. Homogeneous solution. Actually, we can write it directly because we already know YH is here, right? YH is here, has 2 poles, so we can just use these 2 poles. So these should be A plus BJ. Okay, this A, B are different with that A and B. I use alpha beta. Alright, it's alpha plus beta J times the first pole is 1/2 plus 1/2 J to the n. Actually, just this one, right? Just this one. Here's the same thing, but no U of n. Right? Here's you have U of n. This is no U of n, and the coefficient now is alpha plus beta J. You need a use condition, the initial condition to determine that, but so far we don't have. And this is first one, and second one will be plus alpha minus beta J, and 1/2. The second pole is here is a negative. Okay, all right. Then we have all possible solution. Is YR equal to YH of n plus YP of n. Here alpha beta, they are any real number. Alright, so we work like this. You work like this. Okay. Yeah. Alright. That's all for today. Then see you next time.